Hello all. In kinematics, we learn how to describe the motion rather than concerning with their causes and the explanation of them. In the description of motion, we explore various methods and tools to describe the path of motion and how slow or fast the body moves. Now we learn the concept of position, distance and displacement. When a body keeps going from one place to the another, we say that it is in motion. It never happens that a body disappears from one place and reappear at the other place. For example, body is here at one instant and at a later instant it disappear and reappear at some other place. It never happens. The body has to travel a continuous path from its initial position to reach its final position, and it takes time. As shown, the body follows a path to reach its final position, and at the same time the time passes. The body takes the time from T1 to T2 to go from initial position to the final position. The change in the position of a body with time is called motion. The distance traveled by the body is the length of the path along which the body moved. The distance traveled by the body from one place to the other may differ depending upon the path followed. For example, a body moves from point A to point B along the path shown. The distance is d1, which is simply the length of this path. Another path from A to B. The distance is d2. This path is longer than the previous one. This is third possible path, which is longer than the previous two paths, so greater distance. And this is the straight path from A to B. So we see that given two positions, there are various paths by which body can go from initial position to the final position. So it may travel different distances. So given the initial position and final position doesn't mean there is just a single way that the body can go from A to B and there will be a single value of distance. This is not so. The distance, however, may tell you nothing about the following. Exactly which path the body travels along, how far it has moved from its initial position, where its final position is, in which direction it started. For example, a body moves along this path from initial position to final position. There is another path by which it can go from the same initial position to the final position. This is the third path, and this is the fourth path, and this is fifth path. All these paths have same length, means body has traveled same distance, but it will not tell you, distance will not tell you exactly which path is followed because many paths are possible as shown here. How far it has moved, we have no information about how far the body has moved when we know the distance. For example, if the path is straight line, then the body will be furthest from the initial position, and if the path is, for example, as shown here, then the body is closest to its initial position. These two paths have same length, but when a path is straight, it is furthest, and when path is like this, it is closest to its initial position. We cannot know where its final position is. So all the distances are same, but the final positions are different. So we cannot know exactly where it is its final position is, in which direction it started. So as we can see that we cannot know in which direction body started. Body may have started in any direction. So the distance does not tell us about all these facts. However, distance may help you know, for example, how much petrol have been consumed by your car or the calories you lost, because the petrol consumption depends upon how long the body has traveled, how longer or shorter path the body has traveled. Same is the case about our calories. How much calorie we lost depend upon how long path we have traveled or how small the path is. The displacement. Any arbitrary curve, the path of motion, may be represented simply by the series of sufficiently small straight line segments drawn along the curve. So here we see there is an arbitrary curve path, and that curve path is superimposed with the series of straight line segments. If we view the original path and the straight line segments separately, we see that on comparing the series of line segments with the original curve, we find that the line segments do not fully resemble the curve. These line segments do not fully resemble the curve. On taking still smaller line segments, the series would look more like the original curve than previously. So now we are taking smaller line segments and superimposing it on the original path. Now we separate the two and we compare the original path and the series of straight line segment. So with smaller straight line segment, the series of lines look pretty much like the original path. If you go on shortening the line segments, the picture would be more and more like the original curve. That is, the limit of the process is the exact copy of the original curve. That is, in every next step, if we shorten the straight line segments in the series, then the series of straight line segment will look more and more like the original curve. And if you go on doing this from one step to the another and create a series of infinite steps, the series of line segment will look more and more like the original curve. Thus, any arbitrary path of motion may be described as the series of sufficiently small straight lines. Now suppose that an object is being pulled simultaneously in two directions. Which way will it move? When force F1 acts alone, the body moves in the direction of the force. Same is true for the force F2. It is interesting now to see how the body moves when it is being pulled in the two directions simultaneously. Obviously, the body cannot move simultaneously along both the paths OA and OB. The motion may be viewed as a body moving along OA while the line OA being dragged along the direction OB, as shown. We see that the line OA is being dragged along the direction OB while the body is moving along the line OA. Let's see it again. The body is moving along the blue line while the blue line is being dragged along the yellow line, that is in the direction of OB. Or equivalently, we may view this motion as the body be moving along the yellow direction and the yellow direction itself or yellow line itself is being dragged along blue direction. This is the most reasonable idea to anticipate the resultant motion. The displacement OC may be viewed as the displacement OA and OB taking place simultaneously. Thus, the resultant motion is along the diagonal of a parallelogram formed by the sides OA and OB, both coterminous with the diagonal. coterminous with the diagonal. We state that the displacement OC is the sum of the displacement OA and OB. We write it as displacement OC equal displacement OA plus displacement OB. It must be noted that the length of the line OC is not necessarily the sum of the lengths of the lines OA and OB. That is, the length OC is not necessarily the sum of the lines OA and OB. While length is an ordinary scalar quantity, but displacement is no ordinary quantity. The displacement is added according to a different law. Here we have said the displacement OC equal displacement OA plus displacement OB. Considering that displacement OC is equivalent to the displacement OA and OB taking place simultaneously, the displacement is a quantity which has direction and is added according to the parallelogram law. The quantities which have magnitude as well as direction and added like displacements are called vectors. The direction of vectors is denoted by arrows. The length of the arrow is proportional to the magnitude of a vector it represents. Parallel arrows represent the same direction. An arrow OA, for example, represents displacement from the point O to the point A. It is written as OA with an arrow over it, or OA with a line over it, which we read as OA bar, or by bold letters OA. These are the ways of representing the vector quantities. So here is the parallelogram law. We draw a parallelogram with the two vectors which are being added, OA bar and OB bar. Then a diagonal coterminous with these vectors of parallelogram will represent the addition of two vectors. This diagonal is A bar OA bar plus OB bar. So here we have stated the displacement OA bar plus displacement OB bar is equal to displacement OC bar. It never means that the length of OA plus length of OB is equal to length of OC. The displacement is entirely different quantity because of the spatial attribute of direction. It is not simply added like numbers, but it is added according to the parallelogram law. Let's understand displacement in another context. The two sets of parallel lines, red and yellow, forms a reference frame to describe motion. An object undergoes the displacement from the point O to the point P as shown. Another set of parallel lines, blue and violet, forms a reference frame that moves uniformly relative to the first frame. In the new frame, the objects travel along the fixed L line L. This is the line L, and the object is traveling along this fixed line L in the new reference frame. Let's see it again. An object is traveling along red line, line L. The displacement OP in the old frame may be viewed as the sum of the displacement OA of the new frame relative to the old frame and the displacement AP relative to the new frame. So here the displacement from A to P is relative to the new frame because this displacement is along the fixed line L in the new frame. And O to A, OA is the displacement of the new frame relative to the old frame. And this line represents the displacement of a ball from O to P relative to the old frame. So this displacement OP is stated as the sum of the displacement OA of the new frame plus the displacement AP of ball in the new frame. We write it as OP bar equal to OA bar plus AP bar. Again, the original or old frame. Thus, we define the displacement as the quantity representing the change of position and added according to the triangle law as shown. This is the displacement OA plus the displacement AP equal the displacement OP. We express it as OP bar equal OA bar plus AP bar. This is the triangle law of vector addition. Previously we saw the parallelogram law of vector addition. The triangle law of vector addition is equivalent to the parallelogram law. Here in the diagram we have a triangle and the triangle law states that the displacement OA plus AP equal the displacement OP. Now we draw a parallelogram. We draw a line parallel to the vector AP. Now this is a parallel line, so vector O to B and vector A to P are equal vector. Similarly, the vector from O to A and the vector represented by this line are equal vectors because they are parallel and therefore in the same direction. They have same length, same direction. So according to triangle law, OP bar equal OA bar plus AP bar. OP bar equal OA bar plus AP bar according to triangle law. And according to, we know that the vector AP bar is equal to vector OB bar. So if we replace AP bar by OB bar, we get the parallelogram law that we saw previously. OP bar, which is the diagonal, equal OA bar plus OB bar. The displacement as indicated by an arrow tells us direction and how far the body has moved. However, it has no information about the actual path followed by the body. Neither it has any information about initial position or final position. It only represents how far it has moved and the direction of motion. When we know the initial position as well, we can determine the final position from the displacement. Magnitude of displacement is the length of arrow and the direction of displacement is the direction of arrow. Now we introduce time in our analysis. We start the concept of speed, velocity and acceleration. If a car travels a distance of 3000 meters in 4 minutes, then it travels a distance of 750 meters every minute. The distance traveled per minute is a measure of the speed of a car. We obtain speed as follows. We simply divide the distance of 750 meters traveled by the time 4 minutes taken and we get 750 per minute distance of 750 meters per minute is travel, and this is the measure of how fast or how slow the body moves. So if d is the distance traveled in time, then we simply divide the distance d by the time as we have done here and obtain the speed. So distance divided by time gives us the speed, the distance traveled per unit time. The speed is the distance traveled per unit time. Per unit time means every 1 second or every 1 minute or every 1 hour or every 1 day, whatever. A unit time is the time represented by the number 1. So it could be 1 hour, 1 second, 1 minute, whatever, depending upon what unit we use for measuring the time, whether we measure the time in minute or we measure the time in second or in hours and so on. In the example of car, we assume that the car traveled uniformly, that is, without speeding up or slowing down for the entire duration. If the car speeds up or slows down or halts at some occasions, then the speed calculated from the formula is the average speed for a given duration. So the average speed is actually the total distance divided by time taken, and it gives us a unique value for the speed. But it doesn't mean that an object traveled with that unique speed for the entire duration, for the entire course of motion. It may have slowed down, it may have speed up, or it may have halt at certain occasions. But if we take a total distance and divide it by total time, it only gives us a rough idea of how fast or slow the body moved for during the entire time. The speed may vary with the time. The average speed tells us nothing about the instantaneous course of motion. We can find the speed exactly at a certain moment of time by using the following procedure. Before we consider the procedure, let us consider uh, what is meant by the speed exactly at a certain moment. Consider a simple phenomenon of free fall. If an object falls, it falls with increasing speed because of the gravitational pull. So if falls a certain distance, and if I ask what is the speed with which the object is falling, the question is not appropriate. The question is not fully correct because an object is not falling with the same speed or unique speed, but it is falling with increasing speed. So an object have different speeds at different moment. So it has unique value of speed at any particular moment, and the speed changes from one moment to the other. So the appropriate way or the correct way of asking the question is what is the speed of a falling object at a particular moment, because it changes from one moment to the other. So how to find the velocity or the speed of a body at a particular moment, that we are going to discuss now. There is one confusion regarding the speed at a particular moment. At a particular moment, the body is stationary. When body go from one place to other, time passes. But when we consider a particular moment of time, the body is stationary for that particular moment of time. It travel no distance. But speed is obtained by dividing distance by time. And if you only consider the moment of time means zero time. No time pass, and when no time passes, no distance is travel, means both distance and time will be zero and the speed cannot be calculated. This is the confusion that occur. However, what we do is that we allow for some small time interval to pass. Time passes from the moment t to the next moment t plus delta t giving the interval of time between the two moments. And in that small time interval, we find out what distance is that traveled and divide it by time, and it gives us certain value for the speed. This value, however, is again the average velocity calculated for the duration of time delta t. Within this interval of time, the body may travel with different speed at different moments, as it happened in case of the freely falling object. In a freely falling object, however small time interval you consider, there are again various moments in that time interval and it may travel with different speed. The speed changes from one moment to the other. So even if we consider a small time interval and calculate the speed according to this formula, it is not the speed of the body at the moment t. We have to calculate the speed of the body at the moment t. So what we expect that we will get the speed of the body exactly at the moment t by taking the time interval smaller and smaller and smaller. If we go on decreasing the time interval delta t, then we will get different values of speed, and those different values of speed may be expected to approach certain limit value, and that limit value represent the speed of the body exactly at the moment t. So let us outline this procedure. Suppose that a body travels along the path shown. We wish to find the speed at an instant of time t when the body is present at the point A. This speed is called an instantaneous speed at the time t. Let s be the distance travelled from the origin O in time t. Now time t and instant t are different things. This particular point represents a moment of time t, and t represents the time interval from the time when the body was present at the point O to the point A where the body approached later after the time t. So time t represents this moment as well as the time interval from the point position O to the position A as the body travels from one position to the other. To find the speed at an instant t, we measure the distance travelled in a short time interval from time t to t plus delta t1, and let this distance travelled by the body be delta s1. We allow for the time to pass and the body travels the distance delta s1 shown by the red line till the next moment t plus delta t1. Time pass during this motion is delta t1. The average speed in the time delta t, it is delta t1, is delta s1 upon delta t1. This is the average speed for the time interval delta t1. This time interval is sufficiently small, but however small time interval we may consider, it will not be the exact velocity at the moment t. Therefore, the only way to get the exact value of the speed at the moment t is to consider the time interval delta t1 smaller and smaller and smaller, so that we go closer and closer to the moment t at which the speed is to be calculated. Although the time interval delta t1 is very small, the average speed calculated is not the exact speed at an instant t. The average speed calculated for the time interval still shorter may be expected to be closer to the speed exactly at an instant t. Now we shrink the time interval from delta t1 to delta t2 to go closer to an instant t and calculate the average speed. Now the average speed is v2 equal delta s2 upon delta t2. We further shrink the time interval to delta t3 in the hope of better approximation to the instantaneous velocity at time t. Now we are closer to the moment t at which the speed is to be calculated. The average velocity now is v3 equal delta s3 divided by delta t3. The smaller time intervals may give better approximation to the instantaneous velocity. We continue to shrink the time interval and obtain the infinite series of values of average speeds. If the series of values delta s1 divided by delta t1 and so on has the limit denoted by vt, then vt is the instantaneous velocity at time t. Obviously, the body must have certain finite speed at a particular moment. So it is expected that when we calculate the series of the values of the speed by shrinking the time intervals delta t1, delta 2, delta t3, it is expected that the value of the ratio must approach a certain limiting finite value representing the value of the speed at the moment towards which we are moving by shrinking the time interval. By shrinking the time intervals, we are actually moving toward the moment t, and thus the limiting value of these ratios will represent the actual value of speed at the moment t. That value of speed is represented by vt, and we represent this limiting value of the ratios and hence the instantaneous speed as this. The instantaneous speed at the time t is the limit of the ratio of distance travel and time taken as the time interval approaches 0. It is made smaller and smaller. The limit of the ratio delta s upon delta t as delta t time interval tend to 0 is denoted by ds by dt. ds by dt is not the ratio of the quantities ds and dt. It is just the symbol representing the limit of the ratio as delta t tend to 0. ds and dt are infinitesimal changes and therefore they are not a definite number. Their values is not represented by a definite number. They are infinitesimal changes because ds by dt is just the way of expressing the fact that it is the limiting value of the ratio of distance and time as delta t tend to 0. So we should not confuse this expression as the ratio of some finite value of ds and finite value of time. Here we do not stop at any finite value of distance or finite value of time, but we are generating the process in which from one step to the next we are decreasing the time interval and we are generating the series of values of this ratio, an infinite series which is expected to have a certain limiting value. Thus instantaneous speed is, we can write instantaneous speed also as ds by dt, writing this symbol for this expression of limit delta t tend to 0 delta s upon delta t. The displacement per unit time is called velocity. It is a vector quantity. In speed, we had a distance in place of displacement, and distance is a scalar quantity because it is simply the length of a path. But velocity is similarly defined as displacement per unit time, displacement divided by time. The velocity is added just like the displacement according to the law, according to the parallelogram law or the triangle law, because velocity is simply the displacement per unit time. Historically, the addition of velocities was conceived by Galileo. If the displacement of the body is delta s bar in the time delta t, the instantaneous velocity of the body at an instant t is given by the limit of the ratio of displacement divided by time as delta t is made 0. Suppose that the body travels along this curve path. It goes from the position A to position B. The distance is the length of the path from A to B, the length of actual path, that is the distance. While the displacement is given by the length of the straight line connecting A and B. So distance and displacement are dissimilar as can be readily seen from the figure. However, if we go on decreasing the time interval from the moment the body was at A and the moment the body is at B. Suppose at time t it was at A and at a later time t plus delta t it is at B. So if we go on decreasing the time interval, make it smaller and smaller and smaller, the displacement will look like this. This is the displacement at a shorter time interval. If we decrease the time interval again, we get this displacement and then this displacement and so on. So what we see, as we shrink the time interval delta t, as we make it smaller and smaller and smaller, the displacement delta s bar also becomes smaller and smaller and smaller, and the distance also becomes smaller. However, the displacement, that is a straight line, becomes so small that it almost merge with the actual path of a body. The displacement becomes so small that it almost merge with the actual path of the body. An actual path represents distance and the displacement represents straight line. But when the straight line is very small, it almost merge with the actual path of the body. Means distance and displacement, they become almost equal to each other when delta t is made smaller and smaller, which causes the displacement also to become smaller and distance also to become smaller. So as delta t is made smaller and smaller and smaller indefinitely, we will get the displacement nearly more and more equal to the distance. So distance and displacement become nearly equal to each other when delta t is very small. And when delta t is indefinitely small, we get instantaneous speed. The instantaneous speed is given by delta s upon delta t as limit delta t tend to 0. and the instantaneous velocity is obtained by dividing the displacement by the time. So bar represent displacement and absence of bar represent the distance. But when delta t is made very small, the distance and displacement become nearly equal to each other, and therefore the instantaneous speed and the instantaneous velocity become equal. Because when we make delta t smaller and smaller, we get instantaneous measure of speed and of velocity, and instantaneous speed and instantaneous velocity are equal in magnitude because distance and displacement become indistinguishable concept. Suppose that an object moves uniformly along the straight path drawn on the ship floor. The ship is cruising uniformly on a calm sea surface. What is the path of a body relative to the ground frame? The straight line represents the path of a body or an object on the ship floor. So object moves along the path from A to B on this arrow on the ship floor, but the path of an object relative to ground is shown by this yellow arrow. We check it again. The yellow arrow represents the path of a ball relative to ground, while the pink arrow represents the path relative to the ship floor. Red line represents the displacement of ship relative to the ground. So here we have OA, the displacement of ship relative to the ground, OB, the displacement of object relative to the ground, and AB, the displacement of object relative to ship floor. So velocity of object relative to the ground will be OB divided by the time taken. OB is the displacement relative to the ground, and this displacement divided by the time taken gives us velocity of an object relative to ground. Velocity of the ship relative to the ground is the displacement OA of the ship divided by time t. And the velocity of the object relative to ship is the displacement AB of the object relative to ship divided by the time. And we see that these displacements are related by triangle law of addition. OB bar is equal to OA bar plus AB bar. Dividing both the sides of equation by time, we get this equation. And the next equation simply represents the equation for velocity. So the velocity of object relative to ground is equal to the velocity of ship relative to ground plus the velocity of object on ship or relative to ship. The direction of velocity is the same as the direction of displacement. So this is the red arrow represents the displacement of ship, and the direction of velocity of the ship will be also the same. Galileo's idea of velocity addition constitutes the law of velocity addition. We say that the velocity of an object relative to the ground is the sum of two velocities, namely the velocity of a ship relative to the ground and the velocity of the ball relative to the ship. The ball is moving on the ship. In the diagram shown, the velocity v3 is the sum of the velocities v1 and v2. Galileo's scheme of velocity addition also constitutes the concept of relative velocities. Suppose the reference frame 2, for example the frame attached to the ship, travels uniformly relative to the reference frame 1, for example the ground frame, with the velocity Vr. A body travels with the velocity v2 relative to the frame 2, then velocity v1 of the body relative to frame 1 is given by velocity of the second reference frame plus the velocity of the body relative to the second reference frame. This sum is the velocity relative to the first reference frame. So V1 is the velocity of the body relative to first reference frame, and it is sum of the velocity of the second reference frame which move relative to the first plus the velocity of the body relative to second reference frame. If Vi is the initial velocity and Vf is the final velocity, then we can write Vf equal to Vi plus V according to this triangle. The velocity V represent the change in the velocity from Vi to Vf. The velocity Vi is the change in velocity. That is, when this velocity is added to the initial velocity, we get final velocity. We express this as the change in velocity is Vf minus Vi. What we have done, we have simply added the negative of Vf, the opposite vector on both sides. So this become 0, and here we have Vi minus Vf. Sorry, we have subtracted Vi from both sides. Subtracting the vector means adding the opposite vector, a vector having opposite direction but the same magnitude. So Vi cancel and we get V equal to Vf minus Vi. This equation defines the subtraction of vectors. So we can conceive the subtraction of vector like this. This is the velocity V, final velocity. We subtract the initial velocity from it. Subtracting the initial velocity means adding the opposite velocity. This is the velocity Vi bar. The opposite velocity will simply have the opposite direction and the same magnitude. This is minus Vi. Opposite direction and same magnitude, same length. And then Vi plus minus Vi. Sorry, Vf. This is Vf plus minus Vi, which we write as Vf minus Vi. This gives us this vector according to triangle law of vector addition. Vf plus minus Vi equal the vector V bar. This vector is parallel to this line and therefore this line represents the same vector V bar. So we write V bar. So change in velocity is simply the final velocity minus initial velocity. A man traveling towards east at 8 km per hour finds that the wind seems to blow directly from the north. On doubling the speed, he finds that it appears to come from the northeast. Find the velocity of the wind. Note the north direction, and we take the unit vector I cap towards right and the unit vector j cap in the upward direction. These balls represents wind flow relative to the ground, and the velocity of wind flow relative to the ground is represented by yellow arrow. And the wind flow, here we see that the balls appear to arrive along this pink straight line to the man. This ball represents man. We again see it. This ball represents a man that is running with the speed of 8 km per hour. The balls hit the man along this line, this pink line, and therefore to man the wind seems to flow from north. The pink line represents the wind flow from the north direction. This pink arrow represents the velocity of wind relative to man. So for a man, the wind is flowing from north because balls appear to hit him directly from the north. Ball represents wind. So velocity of man is 8 I cap because the man is moving towards east with the speed of 8 km per hour. So it is 8 I cap. Velocity of man relative to ground. This is the wind velocity relative to ground, and this is the velocity of wind relative to man, this arrow. So here velocity of man relative to ground, and then velocity of wind relative to the man, and this is the velocity of wind relative to the ground. So according to the concept of relative velocity, the velocity of wind relative to ground is equal to the velocity of man relative to ground plus velocity of wind relative to the ground. This is simply the equation of relative velocities. So velocity of man relative to ground is 8 km per hour, while the velocity of wind relative to man, it is in the opposite direction to j cap. So opposite direction to j cap is simply minus j cap. Okay, and the velocity may be written as minus y times j cap, y representing the magnitude of velocity of the wind relative to man. Now when man double his speed, the wind velocity relative to the ground is not affected. So you see the balls moving in the same way. So when the speed is double, the wind appears to hit the man from northeast direction. Northeast direction means the direction midway to north and east, making an angle of 45 degree with east and north. That is with the vector I cap and with the vector j cap. A man has double speed, and this pink line represents the direction in which the balls hit the man. That represents the direction of wind flow as observed by the man. So balls are hitting the man along this pink line. So direction of wind velocity is midway between the east and north, that is the northeast direction. The velocity of the man relative to ground is now double, which is 16 times I cap, and the velocity of wind relative to man is now represented as V dash bar. Let's check it again. Okay. So this is the velocity of the man relative to ground, which has been doubled. This is the velocity of wind as seen by the man, and this is the velocity of wind relative to ground. This dotted line represent the velocity of wind relative to man in the previous case when the man traveled with the speed of 8 km per hour. So this much distance, the angle is 45 degree. The angle made with the direction I cap will be 45 degree because I cap is the east direction, j cap is the north direction. And now the wind appear to flow from northeast, means the direction making an angle of 45 degree with east or north. So this direction is a 45 degree. So again here we have a relative velocity equation. The wind velocity relative to the ground remain unaffected irrespective of how fast or slow man move. So wind velocity relative to ground is equal to velocity of man relative to ground plus the velocity of wind relative to man. Man's velocity is now 16 I cap. Now distance AC and CB is equal because AC represent previous velocity and AB represent the velocity at the present moment, which is double. So AC is 8 km per hour, so BC is also 8 km per hour, means the magnitude of BC is same. Now this angle is 90 degree. So in this triangle, I write D here. So in the triangle CBD, one angle is 90 degree, other is 45. So obviously this angle will be also 45. So it is equilateral triangle, and therefore the sides in front of 45 degree angles will be equal. So side BC and this side, which represent man's velocity in the previous case, these two sides are equal. So what does it mean? That the magnitude of man's velocity, wind velocity relative to man in the previous case. So VWM is simply minus hj cap. See, VWN, wind velocity relative to man in the previous case, is simply equal to CB, because this triangle CBD is equilateral triangle. So VWM equal CB equal 8 km per hour. This means that Y value is 8. Now we have seen already that the wind velocity relative to ground is 8 I cap minus yj cap. You may go back in the video and check this equation. We have now discovered that y is 8. So substituting 8 for y, we get wind velocity relative to ground to be 8 times I cap minus j cap. That is the final answer. Let us see the two situations together. When man traveled with the speed of 8 and then double his speed to 16. So this direction represent the man traveling with the speed of 8, while this oblique direction represent the man traveling with the double speed 16 km per hour. When man was traveling with 8 km per hour, the wind appeared to flow directly from north, but at double speed the wind appeared to flow from northeast direction. The initial velocity is v bar at time t, and it changes over the time interval delta t to the final velocity v bar plus delta v bar at the later time t plus delta t. So change in velocity is delta v bar, and time taken or time interval pass is delta t. And acceleration at an instant t is the change in velocity per unit time. This is an instantaneous acceleration at time t. So acceleration is simply the change in velocity per unit time. It represents how fast or slow the velocity changes with the time, and it is an instantaneous acceleration when we shrink the time interval smaller and smaller indefinitely. Uniform circular motion. The motion of an object moving along circular path with the constant speed is called uniform circular motion. In uniform circular motion, though the speed is constant, the velocity changes continuously in direction while the magnitude remains constant and is equal to the speed. Instantaneous values of velocity and speed are same, whatever the path or whichever the way the body moves. The instantaneous velocity is tangential to the circular path. These arrows represent direction of instantaneous velocity and also its magnitude. Instantaneous velocity direction is always tangential to the circular path because velocity is always in the direction of displacement. But when we consider instantaneous velocity, the displacement will be very small because time intervals considered are very small for calculating the instantaneous velocity. Time interval approach 0. So as the time interval approach 0, the displacement will almost merge with the tangent to the circle. We get the series of displacement, smaller and smaller displacement when we decrease the time interval, and this series of displacement tend to become aligned with the tangent to the circle. The tangent drawn at a point which coincide with the moment t of the time. So velocity is always tangential to the circular path. It is not only tangential to when it is only a circular path, but whatever the path, whatever the curve path it may be, the instantaneous velocity is always tangential to the path of motion because displacements almost merge with the tangent to the curve path. And velocity is always in the direction of displacement. So instantaneous velocity is always tangential. Suppose that the particle is at the point A on the circle of radius r at the time t. R bar is the position vector of the point A drawn from the center of the circle. It is also called the radius vector. V bar is the velocity of the particle at a time t. As the particle moves along the circle, it reaches the point B at a later time t plus delta t. The radius vector rotates through an angle delta theta to the new radius vector r bar plus delta r bar. It is called an angular displacement of the particle. The velocity at the time t plus delta t is v bar plus delta v bar, which we have denoted as the final velocity, and this velocity v bar is the initial velocity. In uniform circular motion, the magnitude of velocity remains constant, means initial velocity, final velocity both have equal magnitudes. We should write these velocity vector symbols between two vertical lines because that is the way we represent its magnitude. The change in velocity is delta v bar, time taken is delta t, the displacement is delta r bar. We shift the velocity vectors to find the change in velocity. According to the triangle law of vector addition, the change in velocity is given by an arrow qr. This velocity adds to the initial velocity and gives us the final velocity. The radius is perpendicular to the tangent at its foot on the circle. It is well known fact from basic geometry. Angle AMPN plus angle ANPQ is 90 degree. This angle is 90 degree. Also angle QPR plus angle ANPQ, this is also 90 degree. So from this equation, these two equations, we see that the angle QPR and angle AMPN are equal, and this angle is delta theta, the angular displacement. So angle QPR is also delta theta. The triangles AMPQ and the triangle QPR are both equilateral. This triangle and this triangle. Not equilateral, they are isosceles triangle. Only two sides are equal. The two triangles are isosceles. Two sides are equal because these two sides are simply the radii of circle. They are same, and these two sides represent initial and final velocities. Their magnitudes are same, therefore arrows will have same length. So two sides are equal. Also we can see that these two angles are equal to each other because it is isosceles triangle. They are the angles in front of equal sides. Similarly, these angles are the angles in front of equal sides, so they are also equal. But how do we know that these angles and these angles, these two angles are from one circle, one triangle, and these two angles are from the other triangle? So these angles are equal. Here the angle AM and N, the angle AM plus angle N plus angle delta theta for this triangle MPN, it is 180. Similarly, for the another triangle QPR, angle P, angle Q plus angle R plus angle P is 180. But angle P is simply the angle delta theta. We have seen this angle is same as this angle. but these two angles are equal. So we can write 2 times the angle AM equal 180 minus delta theta. Here also Q and R are equal. So we can write 2 times the angle Q equal 180 minus delta theta. So these are both 180 minus delta theta. So these two angles must be same. Angle AM must be equal to angle Q. But angle AM is also equal to angle N, and angle Q is also equal to angle R, and we get this equality. So what we see that all the three angles of these two triangles are equal to each other correspondingly. So these two triangles are similar to each other. They are not congruent, but they are only similar to each other. Means their corresponding sides have same ratio. That is, by similarity we mean if the side PM is 3 times the side PR, if it is 3 times the side PR, then the side PN will also be 3 times the side PQ, and the side delta R will also be 3 times the side delta V bar. This is one. So here we have to pair the sides of the triangle in a proper way. Only corresponding sides have to be taken together. For example, this angle delta theta correspond to angle delta theta. So only the sides in front of these angles will compare. The side delta R bar will compare with side delta V bar, and delta R bar side is 3 times the delta V bar. Then the angle AM is equal to say angle R. So side in front of angle AM, which is this side, it will compare with the side in front of the angle R, which is this side. And if the first pair of sides, this side and this side, had the ratio 1 to 3, then other corresponding sides, it means this side and this side, they will also have the ratio of 1 to 3, and the remaining pair of corresponding sides, which is the sides in front of the angle N and in front of the angle Q, these sides will also have the ratio of 1 and 3. So ratio of all the sides is same. So ratio same means their fractions are same. We note that the two triangles are similar to each other. So we consider the pair of corresponding sides from the two triangle and their ratio. The side QR divided by the corresponding side MN of the bigger triangle, and the side PQ of smaller triangle, and the corresponding side PM of bigger triangle. We take their ratio. Their ratio must be equal. That is why we have QR upon Mn equal PQ upon PM. QR represent the magnitude of change in velocity. Mn represent the radius of the Mn represent the displacement of the particle delta R bar. PQ represent the initial velocity, which is V. Initial and final velocity, they both are same, while PM represent the radius. So we write R. We multiply both sides by delta R and get this equation. We divide both sides by time taken, delta T. The velocity magnitude and the radius, they remain constant for the uniform circular motion. So we simply divide delta T by delta T. We only divide delta R by delta T. Delta R, which is the displacement, it is variable. It varies with time as the particle move along the circle. Now we take limit. We shrink the time interval delta to indefinitely smaller and find out what is the limit of this ratio, change in velocity and time taken. So limit of this ratio means the limit of this right hand side. Now as we shrink the time interval, as we decrease the time interval indefinitely towards 0, it does not affect the velocity, the magnitude of velocity or the radius of the circle. As I said, the magnitude of velocity and radius of the circle remains constant with the time. They do not change with the time. So they are not affected when we decrease the time interval delta t. They every time they remain same. So we do not. So limit does not apply to the ratio of these constant quantities. Now this is the displacement, magnitude of displacement divided by time, and displacement divided by time, its limiting value as the delta t tend to 0 gives us instantaneous velocity at the beginning, because when delta t is tend to 0 we are approaching the moment where we began. So velocity, this ratio represents initial velocity, the magnitude of initial velocity, which is simply v. We do not write vi because velocity remains same every time. And finally we get the acceleration, the magnitude of acceleration as v upon v square upon r. This left hand side representing the rate of change of velocity with the time as the time interval approaches 0. This is the instantaneous acceleration. Thus uniform circular motion is an accelerated motion. The magnitude of acceleration is given by this formula. So even though the particle is moving with constant speed along the circumference of the circle, but it has an acceleration as the velocity is changing its direction. And to change the direction of velocity, we need additional velocities to be superimposed on the particle. Now, after the time delta t1, we have this picture. Particle is present here. This is the velocity vector at the final moment. This is the initial velocity vector, and these two vectors have been brought here to find out the change in velocity. Change in velocity is delta v1. We have determined the acceleration in the uniform circular motion. Now we have to find the direction of acceleration. The direction of acceleration is always in the direction of change in velocity, because acceleration is a change in velocity per unit time. So whichever direction the velocity changes, the acceleration is in that direction. For example, this is the direction of change in velocity. It divided by time will give us acceleration, but this is just an average acceleration which is calculated over the time interval delta t1. We want to know the acceleration exactly at this moment, that is the instantaneous acceleration, and for that we will have to shrink the time interval so that we move closer and closer towards the moment t where the acceleration is to be calculated. Now we consider the situation when we decrease this time interval. Now time interval is decreased to delta t2. The angular displacement also decreases to delta theta 2, and this is the situation which is pretty much similar to the previous one. We again decrease the time interval to delta t3. The angular displacement also decreases, and this is what the situation is. We note that the direction of change in velocity is changing as we decrease the time interval. The direction of velocity is shifting towards right. We further decrease the time interval and we see that the direction of change in velocity has further shifted towards right. We see that at the time delta t approach 0, the angular displacement also approach 0, and because the triangle QPR is an isosceles triangle, the vector delta v bar will tend to become perpendicular to v bar in the downward direction, that is opposite to the radius vector. So as I said, as we shrink the time interval, the angular displacement decreases, and because these two sides are equal, the change in velocity vector is shifting more and more towards right and becoming more and more perpendicular to the initial velocity vector. So if you continue to decrease the time interval, finally the change in velocity vector will become perpendicular to the initial velocity. Moreover, it will be directed downward, that is opposite to the radius vector. Since the acceleration is in the direction of change in velocity, it is also perpendicular to the instantaneous velocity at the moment t. Moreover, it is directed downward toward the center of the circle. This is the direction of instantaneous acceleration because this is the direction towards which the change in velocity vector approaches as we decrease the time interval indefinitely. So, in uniform circular motion, the acceleration is directed toward the center of the circle, opposite to the radius vector. It is thus known as the centripetal acceleration. Thank you.